Okay, hello everybody. In this brief lecture, we will slowly introduce the concept of a vector space, the properties associated to a vector space. We define the idea of a norm and also the idea of a metric on a set or a space. So to begin with, let's just have some small slide on the notations, right? So the way we distinguish between scalars and vectors is just with the bold and then the regular letters. Um, so, for example, AI would be the ith element of a vector A. Length of the vector is simply denoted by the modulus of it. Similarly, for matrices, we have notations of capital letters bold A and bold B. Similarly, we have notations for the ith row and the ith columns, and small a's would just denote the ijth element of a matrix A. Okay, sometimes we may not follow this very strictly whenever it is obvious. Okay, so to begin with, begin with on the idea of a vector space. So by definition, it's a set of vectors and a field of scalars equipped with two binary operations, right. So the vector addition, which is defined on the elements in V in such a way that it is closed under addition, that x plus y will give me another vector which is also in V. So this is closed under addition. It is also closed under scalar multiplication in a way that if I take an element from a field F, in this case it or simply we can just say the real line R multiplied with it with x, I still get an element of V. So it is closed under vector addition and also closed under scalar multiplication. Okay, are there a little more rules that these two operations need to satisfy? Okay, so first is this may look pretty simple, but it's nicer to do it again. So commutativity, I add two vectors x and y, it's the same as adding y and x in the reverse way. Associativity, if I have y plus z and then I add it to x, it's the same as I do the operation on x and y first and then go to z. The zero vector, there is a unit vector which we call as a zero vector, such that if I add the zero vector to the vector x, it will give me the same vector x again. There is also, so this is called the additive identity. Okay, similarly, there is a negative vector such that if I take x, the negative of it is minus x, I do the vector addition and I get a 0. So this minus x is called the additive inverse. Okay. Then there is also something called a vector 1, such that 1 times x will give me back x. So this vector 1 is called the multiplicative identity. Okay. Then few other properties which follow. If I take two elements C1 and C2 belonging to the field F, then the multiplication of C1 with C2 times x will give me the same as if I do this operation first and then multiply by C1. Then you have the distributive property, C acting over x plus y will give me Cx plus Cy, right. And similarly, if I take two elements from the fields C1 and C2 acting on x, that will give me C1x plus C2x. Okay, so these are the 8 properties that we need to check given a certain space is a vector space or not. So okay, so by the way, so this one is just it's not a vector one, but it just comes from the field, right, from F. So this is a little typo here, but the multiplicative identity like still holds, right. So it's a consequence of this scalar multiplication stuff. Okay, so some examples of a vector space. The 0 vector is definitely a vector space. You can check all these operations. Rn is a vector space over R. Similarly, I can also say that Cn is a vector space over C. Cn is the set of complex numbers. or the space of complex numbers. Interestingly, Cn is also a vector space over the real line. You take a number from the real line, multiply it with a complex number, you still get an element which is in Cn. However, interesting is the following. So, if I take R, this is not a vector space over C, right. So, if I take C, multiply with an element in R, I get an element outside R and I get an element in Cn. So, this is like not a vector space. Similarly, I have R m cross n, the space of matrices is also a vector space over R. I can take a scalar, multiply it with a matrix, I can add two matrices and so on. All these 8 rules can be verified easily. An interesting example is also the set of functions, right, continuous functions that map an interval of the real line, this could be the entire real line also, to Rn over the field R. Right. So, mathematically or can I say this, the continuous functions that map an interval of the real line to Rn is mathematically written in the following way. So, what are the properties I need to check for this? Take two functions f plus g acting on x, I will still get f of x plus g of x. Right, this both are in R. So, I am just adding up those numbers in the real line. Say as good as saying take e power x plus x cube could be a simple example of this. Similarly, I take a scalar c, f over x is the same as c f of x. Okay. I will also have the 0 function, f x plus 0 will give me f of x. Similarly, I will also have the negative of a function, f of x plus minus f of x is 0. Okay. And then I will have the number 1 multiplied by f of x will give me the same function back. So, I can just write down all the set of rules and verify that the set of functions that map say interval of the real line to Rn is actually defines a vector field. Okay. Things that are not vector spaces are the following. So, if I take x and y or in R2 and restrict x to be positive. So, the area of interest here is this one. You can easily see that this will not constitute a vector space because minus x is not an element of this vector space and so on. So, some of those properties will fail. Similarly, if I take in the second example say y equal to 1, say this real line. This line here is also not a vector space obviously because some of those properties like would fail. And I can then keep on drawing these lines. So, say for example, lines which go this way or this way, they will also not constitute a vector space essentially because they do not also pass through the origin. So, the 0 element is not a part of this and it is neither a part of this space defined by these expressions. Okay. So, continuing to introduce few more concepts. So, we define the notion of an inner product vector space which we also learnt as the dot product, right. So, it is vector spaces in which inner or dot product is defined apart from vector addition and scalar multiplication as we saw in the definition of a vector field. So, any vectors in an inner product space can be combined to get a scalar, right. So, if I take dot product of two vectors x and y, I get some number c where c is in R. Okay. So, this we know this a little from our high school calculus. So, any vector space equipped with an operation like this, the dot product is called an inner product space. Rn is or R3 is a very simple example of that. Okay. The next thing that is important is the idea of a normed vector space. Okay, we are just introducing these concepts, and as we go through the lectures, it will be kind of obvious of why we are defining so many quantities. So, we are just like learning tools which will be useful to us a little later. Okay. So, a norm is a function that assigns a positive length or size to each vector in a space. So, loosely speaking, you can also talk about as in R2 say the length of a vector, so to speak, right. So, just say some p norm, we will denote this as x, this 2 parallel bars with x and 2 parallel bars in p, right. Okay. So, so this norm I can look at it as like again as a map which goes from the vector field, sorry, vector space V defined over a field F and gives values in R plus. So, this is essentially what is meant by positive length here. Okay. So, this norm has to satisfy some properties. So, the norm is usually greater than or equal to 0, and it is 0 if and only if x equal to 0, right. So, that is okay, right. If you just are at the point, the length is 0 if you are just at the origin, right. So, that is the 0 vector. Similarly, there is something called the triangle inequality. I take two vectors x and y, the norm of this will be less than or equal to the norm of x plus norm of y. So, we will derive this in one of the tutorial classes which my TA will be doing it shortly. Similarly, take a scalar c multiplied by x, the norm would be the modulus of c times x of p. So, this is not always necessary that c should belong to R. C should can also belong to the set of complex numbers, where then the mod of c would just be the magnitude of the complex number. Okay. So, just to give some examples of what are norms. So, some of the important norms are like so we start with the one norm. I just draw some pictures to make it a little clear. Okay. So, the one norm is summation of all the magnitudes of those individual xi. Say I say x is equal to say 1 and 2, this is in R2. So, that will be say a 1 here and a 2 here. Okay. So, let us say this is of length 1, this is of length 2 here. So, the norm here would be 1 plus 2, that will be equal to 3. Similarly, if I have 1 minus 2, which will mean that okay, this stretches till here until minus 2, then the norm will still be the same. You will have 1 plus minus 2 giving me 3, and that is the definition of a one norm. I just taking the absolute values of each components and adding them up. 2 norm is what we know as the length of a vector from coordinate geometry. So, in this picture it would mean that, so this is your 2 norm. Okay. So, this is like you take x1 square plus x2 square and then do the square root of it. I can generalize this 2 norm to something called a p norm. And so, here I have this 2, I just replace this 2 by p and I have what is called a p norm. And as I extend this p or take the limit as p goes to infinity, I have something called the infinity norm. Okay, what is the infinity norm? I just take the maximum of all these values, right, maximum of all the modulus of xi. So, for example, in this case the infinity norm would be this 2 in both of these cases, right. So, this the maximum value is 2 and the maximum value here is the mod of minus 2 is still 2, right. I just take the maximum of these values. So, okay, so are these norms, or is it obvious that these are like norms, right. So, we have just defined it, right. So, what should these norms satisfy are properties like this. Okay. So, as a little exercise you can just do it for yourself to check that all these norms 1, 2, the p norm and the infinity norm actually satisfy the properties of the norms. So, the most difficult one is to, or the tricky one is to prove the triangle inequality. So, I just do it for one of the cases and the remaining should be like obvious. So, let us take the infinity norm. So, what I have to prove is the triangle inequality for the infinity norm. So, what is x plus y? The infinity norm of it by definition is max over I, and so what are the components? I am looking at x I plus, or say max x1 plus y1, x2 plus y2 till say if I am in an n dimensional space, I am looking at x n plus y n. Okay. Now, what do I know, right? So, if I take this magnitude of, these are just simply numbers, right, x I and y I. So, this is pretty straightforward to verify that this will be less than or equal to x I plus y I. You can maybe do it for these two numbers here and check that. Okay. So, now I get put it back here, and what I would find is x plus y of infinity is less than or equal to x of infinity plus y of infinity. Similarly, you can check for the p norm, the 2 norm and the 1 norm and so on. Okay. So, what is nice about these norms, and why I say nice is because this will be very useful to us in the future lectures when we are talking of stability and other properties of systems. So, two norms are equivalent, right. So, again defined, both are defined on the same V, and the same way are equivalent if one can be bounded with respect to the other. So, let us just say take these two norms, norm A and norm E. So, equivalence means that mathematically it satisfies a property like this, right, where alpha and beta are just positive numbers. Okay. So, this is obvious. So, I will do an example, and the rest you can check by yourself. So, let us do this for the infinity norm. So, if I just look at the infinity norm and the 1 norm is less than or equal to n times, right. So, this equivalence means something like this holds between the infinity norm and 1 norm, where alpha is 1 and beta is n. Okay. So, let us verify these inequalities one by one. So, x of infinity by definition is the maximum over I of all these xi's. Okay. And what is x1? x1 is summation I equal to 1 to n each of the xi's. Okay. And one of these xi's is the infinity norm. So, let us assume without a lot of generality that the infinity norm, sorry, the infinity norm is just the first element. Okay. So, okay, this it can be second, third, whatever, just for simplicity I am writing it this way. So therefore, x of 1 is now okay, I should do this way, right. Say I equal to 2 to n xi. Now, this is the infinity norm, and then you have some other terms here, and therefore, I can write that the infinity norm here is less than or equal to the 1 norm. That is okay, right? So, this is the 1 norm, this is the infinity norm, and this one. Okay. So, because this guy here is my infinity norm. Okay. So, the first part of the inequality is done. Okay. The second part should be straightforward again, right. So, if I look at the relation between x1 and x of infinity. So, x1 is again I will have the magnitude of x1 plus x2 until xn, and again, so I assume that this is the infinity norm. So, therefore, so I can just write this as x of infinity, and what I know that this is the highest, or this is the largest or the maximum value, therefore, all others will be less than or equal to the infinity norm. Okay. So, therefore, this will be less than or equal to, again, so everything will be just x of infinity, and therefore, I have this is less than or equal to n times x of infinity, right. So, similarly, I can show the equivalence between the 2 norm and the infinity norm, the 1 norm and the 2 norm, but in general in any finite dimensional spaces or where the dimension is finite, that R in R and N is finite, all norms are equivalent, and this will be a very beautiful property, as we will see a little later. Okay, something which is a generalization of a normed vector space, and this maybe if somebody would be familiar with a course on topology, they would have encountered things like this of metric spaces. So, let us start with the set X, right. A metric on X is a function defined on X cross X again to R plus, such that the properties of the distance are maintained. So, I am just defining a distance between 2 points. So, first point is obvious that the distance is usually between 2 points is greater than 0, and it is equal to 0 if and only if 2 points are the same. Okay. Secondly, the distance between point x to point y will be the same as the distance between point y to point x, kind of obvious, right. And of course, something equivalent of the triangle inequality, right. So, distance between x and z will be less than or equal to the distance between x and y and z. Okay. So, how does this relate to the Euclidean space? So, a lot of time to the Euclidean space, how do normed spaces and metric spaces relate to each other? So, let us do something from what we know from our coordinate geometry classes. So, the Euclidean norm of an element is just this number, right, or just the length of the vector, right, or the distance between the vector and the origin. That's the Euclidean norm. Whereas, if I look at the Euclidean distance between two vectors, it is defined this way, right. X distance between x and y is just the 2 norm of the difference between x and I. So, we can say something in general based on these observations, that if I define a norm on a vector space V, then the function d, which is defined in the following way, that dx comma y is the 2 norm of x minus y, is a metric on V, right. So, I have a norm, the notion of a norm. From the notion of a norm, I can define a metric on V, okay. And therefore, I can say in general that the norm vector space is usually a metric space, but a metric space need not have the same properties, right. I am not even talking of a set of a. So, when I look at the definition of vector space, I just begin with a set. It has no properties, it is not a vector space or nothing, it is just some set which has these 4 properties satisfied, okay. So, therefore, I can say that the concept of a vector space is a generalization of the concept of a normed vector space. So, we will do some problems on this in the tutorial classes. So, this was just to introduce you to the concept of a vector space, inner product, the idea of norms and the metric spaces. So, later on we will do something on what is the span of a vector space, the basis of a vector space, is the span and basis the same concept or different, and then we will slowly introduce the idea of a vector subspace. Thank you.